So I'm just going to hand it over to Luke now. As you can see by his title slide, he's actually carried on from a number of other student projects looking at flood flow as well as culvert sizing. So in this case, Luke's actually worked on implementing this within a GIS interface. So Luke, the floor is yours. Time kind of starts now.
Thank you very much, Rian. Firstly, good morning, everyone. Like Rian said, my name is Luke. Firstly, I'd just like to say thank you for all the people on Zoom and people in person who've come along to view our presentations. I know both myself and my colleagues appreciate it, so thank you. So today I'm going to be discussing my dissertation project centered around GIS-based culvert design. So let's start. All right. So why should you be using GIS-based culvert design? Well, it provides a practical solution that gives a structured and repeatable design procedure. So what did I do? I designed 35 catchments in Northland. As you can see in the figure, the locations of the catchments. Now I designed them using my tool and manually, just to aid along the design process. The star there is where Kaitai is located, just for a bit of reference. So I used the rational and TM61 empirical methods, and then I utilized LiDAR, elevation data, land cover database, and FSL soil drainage layer. So my talk today is going to be centered around three main topics. Firstly, the practicality and suitability of using GIS to help design culverts, repeatable results in error reduction, and complications and challenges and improvements. The first two focus on why we should be using it, and the third one focuses on wasn't all smooth sailing. There's a few bumps along the way, as always with all good things. So one of the key measures of practicality is how does it differ from what we have now? Well, simply it utilizes spatial information combined with empirical methods to undertake a design process. Now, it's not just a black box where you click and get a value back. The designer has to step through the process, and after each step, the designer gets back a value, and then the designer can check this value as a reality check, basically. Another key measure of practicality and suitability is whether or not it works. There's a bit of a spoiler on the slide. It does indeed work, and I've got a video here showing part of it working, which is the runoff coefficient variable. There we go. So we've got a mixed land use catchment in Northland here. First step we're going to do is assign appropriate land covers to it. So we do this by clipping the land cover database to the catchment polygon, as you can see here. And the next step we're going to do after this, once it's clipped, so that gives a representation of the land cover. We're going to change the symbology so we can compare the land cover to the under aerial image. And then we can compare to see whether the land covers match up. And as you can see, they match up pretty bloody good, which is awesome. Next, we're going to simulate a fully harvested situation. So we're going to merge all the exotic forests in the catchment together and denote it as fully harvested. You don't have to denote it as fully harvested. You can simulate a partial cut or a fully forested situation if you want to. Next, we're going to use that reclassified land cover, combine it with soil information and slope information. We're going to build up a raster of runoff coefficients across the entire catchment. It's going to change the symbology here to show green's good, red's bad for runoff coefficient. And it allows a reality check the raster does for a designer to look at. And you can see where it's harvested, we have a high runoff coefficient, which makes sense. Then we get a table, which is a weighted average runoff coefficient, and that's the coefficient that we use in design. All right. Alongside providing a cool visual of working, the cover coefficient helped reduce error and was repeatable. So it's a two-step approach, as I just mentioned. You assign appropriate land covers, and then you create your C value or your cover proportions. Now for the cover proportions, there is no value really attributed. You work out the proportions of the land cover instead. So this provides a more structured process which reduces the variability and bias associated with choosing a value over a range. So you get a unique value for the raster instead of choosing between 0.2 and 0.4 per se. And now this gives greater confidence to someone reviewing your design that you haven't chosen like a smaller value just for the sake of it, just for a more economical and smaller culvert design. Another key area that I focused on was getting the TM61 into like a code-based environment. So to do this, I had to find equations for the numerous charts that are available to undertake the process. So I sourced a number of equations from literature, and then I undertook a polynomial approximation of the shape factor. Now, all these worked pretty well, as you can see in the figure. So I checked them by basically calculating the flow rate values for the equations and then the flow rate values for the charts, and I plotted them, and as you can see, they basically fall along that one-to-one line, which is pretty bloody good. It should be noted that for the range that I evaluated them across, they worked well. I followed Costley's suggestion that typically in industry we design for catchments less than 400 hectares, and that's my limitation for these equations basically. I also undertook an approximation of the culvert sizing. Now this proved a bit more variable, on average like 60 mils different and a minimum max of around 100 mils. I didn't really deem whether this was appropriate or not. As I alluded to at the start, it wasn't all smooth sailing, with the flow values produced differing from the manual to the model, as you can see in the figure there. It's generally a well-defined trend showing that the GIS tool produced larger flow rates than the manual method. As you can see, there's one significant outlier on the graph, and that was largely due to the cover coefficient chosen. So if that cover coefficient had been chosen that was similar to the manual method, it would have brought that flow value back into around 40 to 45 meters cubed per second, and that would be more in line with the rest of the trends in the data. However, as you can see, there's still a bit of difference between the that and the one-to-one line, and that was the cause of this difference. The main cause of this difference was attributed to the channel slope. The manual method utilized the equal area and the GIS used the average slope. And this was the main culprit for the difference in the flow values. As you can see in the figure, the equal area method produces a lower slope estimate and the average slope produces a higher one. Additionally, the program uses the longest flow path from the outlet to the edge of the catchment. I use this definition based on the Team 61 statement there included. It may be more appropriate to go to the end of the blue line stream. As you know, from the end of the blue line stream to the edge of the catchment, the terrain steepens up quite significantly, and this can impact the slope associated with the channel. Now, the good news is processes can be adapted in GIS to facilitate both of these. So whether you want to choose the equal area method or the average slope method, you can have it. If you want to go to the edge of the catchment or you want to end on the blue line stream, you can have that as well. All right, a bit more broader look at the slope differences. So I found that my GIS tool overestimated the channel slope. Now, this was compared to the average points method, and I found that there was a simple fix in the code that I could undertake. I just had to change the values that it took to calculate the slope, basically. However, as you can see in catchment 29 there circled, there's still a difference between the equal area method and the average points method. Now, that difference, well, I just explained why that occurs, but that was the main reason for the differences in the flow we observed. So the equal area method produces a lower slope estimate in terms of a smaller flow estimate, and the average points method creates a larger slope estimate and a larger flow estimate. All right, one of the key measures of practicality I had was time. The manual time, design time ranged from 18 to 38 minutes. The GIS design time ranged from 15 to 27 minutes. So on average, I saved about 8 minutes per catchment, which may not seem like a lot, but over 35 catchments is equated to like 4.5 hours, which is kind of significant. And it also should be noted that due to the sheer number of catchments, I got quite quick at undertaking the manual design process. So the actual difference between the GIS tool and the manual time is probably a little bit influenced by that. Sweet, in summary, GIS-based culvert design provides a significant opportunity. There's human error reduction, bias reduction, and consistent design using it. The process is both physically and practically feasible. There are some issues and areas of improvement identified, but this is expected of all new processes, and there's easy solutions to fix up all these areas, basically. Sweet, that's everything I have for you guys today. Does anyone have any questions?
Yeah. Yeah, we certainly do have time for a couple of questions. I'd like to think that this is a pretty handy tool, and we teach a very manual method here at the School of Forestry to the final years for culvert sizing. So if this certainly stands the test of time, we'd certainly like a few people to adopt it and try it out, but we can change our teaching and move towards this GIS environment, which would be a great asset and convenience for our future students as well. Open to questions. Mr. Gilmore.
I'm not probably outside the scope of the project, but thought councils and other organisations would actually like something like this, because you can apply some sort of standard methodology to it, and it's, you know, for a lot of places. So we sort of, you know, you've looked at it from a time saving perspective. You looked at it from other opportunities.
Yeah, like one of the key things I wanted to do as well was create like that repeatable process, because like as soon as a designer undertakes the current process, like the values that they'll get differ from person to person. Like with those TM61 charts, like I found when I was using them, like even the thickness of your bloody pencil lead and the angle that you have your ruler on can like severely impact the result you get. So with those equations, it like reduces that variability almost, and you almost get back to the having like a unique solution for each catchment, which is what you want. Yeah.
Yeah.
Okay. Any other questions?
I think the process you went through to determine the catchment coefficient is pretty cool. Yeah, because there's always a bit of art in that, and rather than science, so actually looking at variables and drilling down is really good. And even if that was only a little tool that came out of it, that would be pretty good.
Cheers.
Hey, sorry, and just maybe Jacob on the Zoom, can you guys hear the questions okay, or is it a little bit hard to hear?
They're a bit light, but no, it's pretty
Okay,
good.
right, yeah, sorry, that's always the problem when you've got an audience in the room. So I will just, Brett specifically asked about, you know, that the councils, the regional councils could be very interested in a tool like this for them, application consistency. And Barry just highlighted the fact that even just that catchment coefficient a component would be a really neat tool to have, even if the rest of it wasn't working. So it was just a slight compliment. One more question, either from the Zoom crowd, anybody within the Zoom audience? Questions?
How are you, like lots of these good things that come out of this, how do you try and promote it? You've done this and that.
So sorry, just the question from Mr. Gilmore was, how is he going to promote it beyond his conclusion of his studies here at the university?
Well, to be honest, I haven't really thought about that. Like I've kind of just gone along and done it, so I haven't really put much afterthought into like the following steps, really, to be honest.
Yeah. Whereby I have encouraged him to give it a name like Luke's flow modeling tool or something like that. You want to have some ownership and some pride in something catchy. So, hey, with that, thank you very much, Luke. Excellent presentation, and we appreciate it. Yeah.